Hi, this is Vaibhav again from TechRail, and this is more or less the method I had thought of for performing encryption of data in Chamber, since we are talking about changing Chamber project here. And I wrote it and I sent the link to a few of my friends, and both online and offline. And those people who could understand, and I knew they could understand, came back saying, at least some of them came back saying that not everything was really clear to them. And this is not the first time this has happened. I have come across a lot of good engineers, in fact great engineers, who know a good amount of engineering, and yet when it comes to security, when it comes to hashing and encryption, and why GPUs can break encryption faster or something like that, uh, they don't really understand. So there are people who understand like 70%, 80% of it, but not everything. There are some people who lack the basics, so everything else they think they understand, but they don't. Anyways, it looked kind of justified to do a small primer on hashing, encryption, and GPUs, and why they are able to break code. And this is a primer, so I'm not going to talk a lot about it. If you find jargon or things that are not really well explained, you can reach back. Or you can start searching on Google, whatever suits you. I would definitely recommend you search on Google first, try to understand things yourself. This is just a primer, and I have watered down the concepts, you know, really heavily. So what I'm going to show here is not a practical thing. It just represents more or less the idea of what happens in a real world scenario. And I'm going to walk you through a few steps of what and how things work, and why people use strong encryption, what are the parameters of a stronger encryption or a better hashing mechanism. So, so that it's clear why we and how we arrived at this point where we use such sophisticated algorithms for solving a problem that doesn't look like a big problem at all. Now, uh, when we talk about hashing, we have to know what hash is. So if I go back and I think I searched, yeah. So this is an example of hashed dish. What do you see in every image? It's a mixture of some kind of stuff, right? Like this is some corn beef hash, this is potato hash, and here you can see I can see some maybe coriander leaves, some cheese grates, there's potato, there is probably tomato. I don't know what spices were used, how much salt was used, and how it was prepared, right? This is the essence of hashing. Hashing has to result in in something which when looked at will not give you a complete idea of how it was prepared. It's jumbled up, it's mixed up, it's mashed. The original structure was completely destroyed, is how hash uh, is supposed to be in real world. And there are different kinds of hashes. There are some hashes that look like cow dung, and those I would say are better representation, because looking at those you can't you I mean even real cow dung could be a good hashing example, because you don't know what cow ate, right? Just it just went through some process and there you have it. Like you can't trace back what cow ate by just inspecting that hash in detail, right? I mean, some people can, but it probably won't be accurate. Now, with that analogy in mind, there is a second principle that you have to take care about. In computing, the input of a hash is usually some kind of a number, because computers operate with bits and bytes, right? They are all numbers in the end. The algorithm is the process those inputs go through, and the result is something which is desired to be in such a state that it is not traceable back. A second subset of that requirement is that if you are given an algorithm and inputs, that input and only that input should result in that hash. If there are different inputs which when go through the same algorithm will result in the same result, will end up with the same result, then it's a bad hashing algorithm. For example, addition. Right? I've taken 17 and 22 as numbers, I've added them, the result is 39. Brilliant. But there are so many other, there are so many other sets of numbers 16, 23, 138, 10, 29. You add these pairs, you get 39. Also, even if you know what addition is, and I don't tell you how many numbers were added, the total number of hash collisions will explode. You can add 15 different numbers and get a result of 39, right? They can be repeated, fine, but you'll get the result, right? So addition, as you can see, is not a good hashing algorithm because of the number of collisions. You cannot use this addition as an algorithm to verify that yes, this input is exactly what produced this output, because there are so many hash collisions. This process of finding, or no, not exactly the process of finding, this phenomenon where different inputs with the same algorithm produce a certain output is called hash collision, and it is very desirable to be avoided. It should be avoided for a hashing algorithm to be used for security purposes, right? If you make this a little bit more complicated, and instead of using addition, we are going to use multiplication. Okay. Now, same number, 17 and 22. 17 multiplied by 22 gives you 374. Lovely. How many hash collisions do we have? 17 itself is prime. So if you were to factor this, you will get 17, you will get 11 and 2. 22 decomposes into 11 and 2. So you have got three possible inputs to reach here, 374. 17, 22, 34, 11 and 187 and 2. These are the three pairs, right? It's still not good. I mean, if you know that this is the result and the input, the algorithm is multiplication, you have got three ways of achieving here. Think about it as a password, right? If usually hashing is used to protect passwords. Passwords are not stored as you input them. They are transformed, they're hashed, and then they are stored, right? If you inputted 17 and 22 as your password and the hash became 374 and someone else tried inputting 34 and 11, although he didn't enter what you entered, right, he'll still get the same result. The hash will match and your account will be open, right? This is how hashing is supposed to be used. So hash collisions are better avoided. What I wanted to show in this step here was multiplication is way better than addition at hash collisions. So in very sophisticated algorithms, it is much likely, it's more likely to find a multiplication operation than an addition operation. You'll see this as you go ahead, not in this primer, but if you research on your own. Now I've invented this another multiplication approach. This just came into my mind. Let's not depend on the basic operations and let's mix and match. Okay, will this result in a better result? Let's see. So what I'm going to do is I'm taking two numbers. Now notice that these two numbers, both for my own use case and for this explanation, are only 2 digits. Okay, and what I'm going to do is I'm going to take the first digit of each one of them, multiply them and get a result. So 1 and 2 multiplication becomes 2, 7 and 2 multiplication becomes 14. Now at this point I have got 2 and 14. Like, how many ways I can create a hash? One way is to reduce these before concatenation. Concatenation is basically appending this thing to at the end of the first one. So I reduce it to just 2 and 14 remains 14. So 214 is the result. The other way is to keep both of these results in their 2 digits form, in which case 02 remains as 02, 14 remains as 14, the result is 0214. Now this is green, this is green. Okay, so I'm going to show hash collisions of this approach over here. And if you know that this is the way it was produced, and I've got 4 digits over here, probably there were 2 numbers and they were both 2 digited. So someone with that information will take 2, try to decompose it. There are 2 ways of decomposing 2. Either the first number is 1 and the second is 2, or the first number is 2 and the second is 1. Either way, this is the total combination. And mix that with 14. There are 2 ways of decomposing 14. The first number is 2, and the second number is 7, or the first number is 7 and the second number is 2. So there are a total of 4 ways in which this mechanism of hashing collides. There are a total of 5 different numbers or pairs of numbers which can go through this approach, and you will get 0214, right? So the numbers are 1722, the original, 2217, 2712, 1227 and 1722, right? Like, oh sorry, this is the one that we used here. So 4 total collisions, 3 total collisions for this input, 4 total possibilities, right? Again, we have got 4 collisions. So just mixing and matching doesn't seem to be giving us results. In fact, if you look at the simple one, we had like 3 options, right? And here I've got now 4. This has become worse. What if I continue this same approach for bigger numbers? Will it be any better? Let's discover that. Now I'm taking the same approach, denoted by this light orange, reddish, I don't know what to call this color, as the operation with 3 numbers. Now in this case, all the 3 numbers are 4-digit numbers. I'm going to multiply the first digit of each number and add or concatenate in the end the result. So 3 into 6 into 5, 3 into 3 into 4, 0 into 7 into 3, and 6, 9 and 2. Okay, 6 into 9 into 2. This 365 becomes 90, and this 334 becomes 36. This, since 0 is involved, becomes 0. 692 becomes 108. Result, this. And if you were to know that this result came out as a result of this kind of this weird multiplication system, how many collisions do you think? There are way too many collisions. Let me just decompose one. Okay. So let's take 090. Someone knows that, okay, this number came as a result of 3 numbers being multiplied. What are those 3 numbers? The first original, obviously 365. 3 into 6, 6 into 5, that's 1. What if 1 into 45 into 2 was involved? This will also go to 90, I guess. What if 9 into 5 into 2 was there? I think this also is going to go to 90. Yeah, there might be more. But the point I'm going to show is this 3, here we had 2 options, here we have got 3. There can be more. Then you can go on 36, 0, and the 0 case is very interesting because you can make any of these numbers 0 and you'll get 0 over here. 108 equally complicated. You will get a lot of collisions. Okay, and let's say if you have got 4 into 4 into 4 into 4, what would that be? 256, right? 256 collisions. What that means is, if you use this approach, this algorithm, of hashing, of converting a number into a result so that it is very difficult to trace back the input, you will have about 256 or more ways of inputting wrong numbers and still getting to this result. What I want to show is increasing the input size does not always result in a good hashing algorithm. Okay. The second thing I want to show is as the number is growing, your hash is becoming larger. This is not how real world hashing in today's modern world works. Okay. I'll get to that. Okay. Now, what if I am going to use pure multiplication? I said this one was better, right? What if I use pure multiplication with the same three numbers? You'll get this as the result. Now imagine I just told that three numbers got multiplied and this number was the result. How many ways are there to achieve this number as a result of multiplying three numbers? This one will always be a factor, probably because it's a prime number. Right? But these two can be decomposed in many ways. Right? This is clearly divisible by 3, also by 2. This is also divisible by 2. I think it is also divisible by 8. Not sure. Okay. So still, way too many collisions are possible. I have not calculated. I don't intend to calculate. But I know that there will be collisions because this is simple multiplication and I can see patterns over here. So even multiplication is not good enough to avoid collisions. It may be better than plain addition, but not good enough. Also, this is a worrying thing. As the numbers, the input becomes bigger, your hash is getting bigger and bigger and bigger. Right? So it is becoming possible to more or less understand what kind of multiplication had been done, what kind of numbers, what were the approximate or larger sizes of numbers that were involved in this algorithm, this multiplication, right? Let's keep that thought aside for now and maybe we'll catch up to that. Now, if I just gave you this number and I told you that I multiplied, the first question is how many numbers? I mean, when you look at the screen, you see three numbers were multiplied. But if I just gave you this number and said, okay, a multiplication resulted into this, there are two questions. How many numbers were there and how big were the numbers? And here is where, kind of the using prime numbers, large prime numbers and multiplying two very large prime numbers becomes such a great mathematical operation. Because to factor a very large number, you have to try out what different, numbers would actually be able to divide this number fully, and only then you get a result. Right? But if the number is very large and you know that it was created by multiplying two very large prime numbers, then it's going to be difficult to reach at the input. Okay. But anyway, that is more of a encryption side. So, okay. Result, there can be way too many collisions, there can be way too many numbers whose combinations will result into this, and in such a case, the number size doesn't really matter. Now, let me introduce you to a new way, and this is closer to what happens in real world today. This is called as, I think it's called fixed block cipher, block cipher. Yeah. What I'm going to do is, I'm going to take four 8-digit numbers. From a human perspective, we think in terms of digits. In terms of computers, these blocks that hashing algorithm reads, they're fixed width by binary numbers, okay, not by decimal numbers. But it's, again, I'm just trying to depict what hashing does. Okay, so the algorithm is very simple. Remember, this is a yellow edge. It is not the same as what I have been doing here. Okay, what this operation means for me is, I take two of these numbers, I multiply them, get a result, and keep only the last 8-digit numbers. So I multiply these two, I get this result, and I let go of the first few, I think there are 6, 7, 8 numbers. I let go of those and I keep this 0580470. Now I have read two blocks. I'm going to read the third block. Do the same operation. Multiply this result with this result. Get a number. Discard the digits except the last uh, 8 digits. Again, take the third. This is actually a repetition. My bad, but okay. Serves just as well to show you the result. Okay. Um, so I take this last number, the result of this previous computation, and the last block. Multiply those, get this number, remove the last, keep the last 8, remove the rest, get this. Now, there might be too many collisions that can lead to this, right? But the question is, and I am not an expert at the underlying complex mathematics that powers the today's world's hashing mechanisms. Not even close. I don't understand a lot of those, but this serves only as an example, and I think it is a good example here. If I give you just this number and I tell you that a multiplication operation with this destructive, I'm calling it destructive because I'm destroying this most significant parts of the results in each step. So this is destructive. Like, I'm letting go of some part of the output. I'm letting go of the first few 7 or 8 digits of these, right? And then we arrive at here. Now, what were the actual numbers that will result into this? You can't really predict because you don't even know what this number was. And it is such a big number that even if you think of this, if you want to try out everything here in this portion, so that you get 2 8-digit numbers whose result ends with 89200680, you will get a hell lot of results. So on this level, at least, it looks like there are way too many collisions. Here again here, way too many collisions. But it also, in a way, makes it very unpredictable to guess what the input was whose output is this. This is a complex one, right? You can't easily guess 4 8-digit numbers which, when multiplied in this fashion, will give you this, right? And this is more or less what happens today. Not exactly, but the underlying thought process is the same. Okay, and that is how you get to your modern hashing mechanism. For example, again, I'm taking SHA 256 as an example, and if I say 256 by 16, 256 by 8, that is 32 bytes. I think there will be 64 digits here. Okay, 1 2 3 4 5 6 7 8 9 10. Yeah, approximately it should be 64 by maths as well. Now, interesting thing about modern hashing algorithms. This apparently is the hash of nothing, empty string, no input. This is the hash. But if you input anything, and notice this size remains the same. If I go on adding more and more and more and more and more and more, okay, and doesn't matter what the length of my input is, the resulting output is the same, right? Interesting things. Look at this. It starts with 1d61. Let me make this a little bit bigger. Okay, I guess this is good enough. I'm here. This is the last one, right? It starts with 1d61 EA, something here, ends with 2633F, right? I'm going to change one character. Look at every single thing changing. See, this is called an avalanche effect. And if I gave you this number, will you be able to figure out what was the input? Very difficult. We are dealing with 256 bits here. Do you know what that result is? If I open the calculator app, and I don't know what that result was, but if I take 2 and let me change the view to scientific, maybe I guess that would be it here. 2 and to the power 256. That many possibilities are there. Okay, and these algorithms are quite sophisticated. To get a hash collision accidentally is very unlikely. You are dealing with a number that is 77 digits long. Okay, um, maybe you should go and look at this, the power of 63, to understand how big that number is. Okay, but that's for a different time. Maybe you can do that on your own later on. I'll probably provide the link to this article and maybe that one as well in the description of this video. Okay, coming back. So this is what happens in hashing. We have to avoid collisions, and we have to make the result so that the input remains not traceable. Okay. Well-known hashing algorithms exist in abundance. MD5, SHA, I showed you one variant of SHA just now. Blowfish, decrypt, etc. are there. So these computations are known already. So one can try brute forcing, and we'll talk about brute forcing. Brute forcing is basically guessing password by just trying again and again and again. Okay. And this is why people in systems ask you to create a long password. So if you have a very long password, it will take a lot of time for someone to, sequentially get there. Okay, that concludes hashing part. Let me get back to encryption. Okay, again, encryption in itself is a very complicated thing. The modern encryption relies on a lot of mathematical properties of different kinds of numbers, primarily prime numbers, and the fact that factoring very large numbers into their factors when the factors are also prime and known to be prime, it's going to be very hard. Okay, and we'll get to that in part. Again, just to tell you, this is a primer. This is only to give you an idea, very very basic idea of what encryption is and how it works. This is not close to what computers do today, and this is only the basics again. Okay, with that, this is one of the most basic encryption mechanisms, and one I think has been used by, I guess, Roman army in the past. Not sure. I think it is called ROT13 because it rotates alphabets. So your alphabets go from A, B, C, D, E, F, G, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, and what this guy says is, now there are 26 characters, right? What this algorithm says is, let's take the last 13 and basically rotate the entire alphabet 13 times. What that effectively does is, you will get the last sequence in the beginning here and the first one in the last. This is enough to make your mind spin, even with simple words. Now, I think I missed one point. Let me clarify that. The purpose of hashing is to make things untraceable back to their origin. The purpose of encryption is to make sure that the input looks like garbage when encrypted, and this, when decrypted, or the same algorithm is reversed, gets you back the original data. The idea here is not to destroy your input. Okay, here we kept destroying the first few significant digits, right? That won't work in encryption. Here, whatever you get when encrypted will have about roughly the same size in output, and it will not be fixed size. Okay, you increase the size of the input, the size of the output will also increase, because we want to get back the data that created the encrypted data. So encryption is for keeping things secret in a way that you're able to get it back. Okay, so this ROT13 is One of those mechanisms, one of the most basic ones. So let's get back to where we stopped, right? So this, when you rotate your alphabet in any direction actually by 13 times, the first half becomes the last half becomes the first half, or the second half becomes the first half. What happens is, in such a scheme, if you take a a word, each letter gets replaced by its corresponding, new corresponding letter in the new positions of this rotated alphabets. So C corresponds to P. Let me use this selector tool. So C corresponds with P. So P. H corresponds with U. A corresponds with N. M corresponds with Z. B corresponds with O. E corresponds with R, and R corresponds with E, right? Chamber becomes this Panzor or something. Vaibhav becomes Invoni. Tekrail becomes Grpiyunvi. I don't know how to pronounce all this. This is garbage anyway, not supposed to be pronounced. Now, if you did the same thing, exact same operation on this encrypted content, P becomes C, U becomes H, N becomes A, Z becomes M, and you can see this is going back where it came from, right? So this, if you look, you apply the same logic again to this, it will become this. So in a way, you could basically have this. This is what will happen. Okay. And I guess this is why this visualization, I think I should have completed it. This is called symmetric. Can you see the symmetry? Take something, encrypt it, apply the same logic, becomes the same thing again for each input. This is why it's called symmetric, right? Okay, so this is a symmetric one. What are the dangers? It is symmetric. 13 to shift, 13 to unshift. You apply the same logic to the input, you get it. Easy to break because the algorithm is too easy. Once you have figured out one word, you have more or less figured out everything, right? It's a one-to-one mapping eventually, because it leaves the patterns behind. As in, if I wrote one single text where Vaibhav appears 5 different times, the encrypted text will have in Vauni, whatever this is, 5 times, right? So it is easy to find patterns, and once you have broken a pattern and you know that these patterns are supposed to be in certain order, you'll be able to break them. The encryption block is very small. You are encrypting one character at a time. So these are the reasons why this is not a great encryption algorithm. I mean, maybe for passing notes in the class, but please don't do this after watching the video. Introducing a little asymmetry. Now this is what I'm doing is not exactly asymmetry. I'm just giving you an idea. This is not asymmetrical. What I am going to do is I have replaced the alphabets. Instead of having rotated them, I have replaced them. How? I still have the same set of alphabets, but I have taken this second part and shifted it right, made a space and put 8 over there. So now, if you see, this is the previous value, you are getting a new value, which is not very different, right? But if you applied the same logic now with this input, and you took A and it becomes N, and N becomes now 8. So if you, okay, let's try to do this, okay, and let's see what it becomes. So P becomes B, U becomes G. Remember, this M is more or less not in the picture. Okay, I'm going to gray it out. Yep, and make it no, not this is fine. Okay, this is not in the picture anymore. This will never appear. Nothing matches it. Okay, P becomes B, U becomes G, N becomes 8. So you will get 8 over here. Z becomes L. Okay. O becomes A. R becomes D. And have we arrived? C, H, A, M, B. What? E. Okay. P, U, N, Z, O, R, D. R becomes what? Wait a minute. I think I messed up a bit. P is B. U is G. N is 8. Z is L. O is A. R is D. And D is Q. See what happened. Does this look similar to this? No. Unlike this, where the same operation when repeated gave you the original text, the same operation when repeated gives you a different text. This does not return back to this. This becomes something new. Let's mark it as maybe this red. This is not what you wanted. You wanted this. So this is a little bit of asymmetry. But this is more or less a replacement. I mean, if you learned the mapping that, okay, every P is going to become, I think I have not created the mapping again, but there will be one, right? And this is more of a replacement instead of rotation. And that's it. So this rotation becomes a little bit of, this replacement instead of rotation becomes a little bit of asymmetry. The same operation applied to the ciphertext does not give you the original one. It gives you something different, right? It is different from this thing. Like these were from the symmetric ones. And just because of this 8 over here, this is totally garbage. Okay, and this is again same thing will happen with these as well. You can predict that, right? So that's asymmetry. Now if you came here hoping to learn RSA encryption, I'm sorry, but I've not figured out a way to express that simply enough. Like I am not even trying for that. But basically RSA when applied, what happens is RSA gives you two keys. One is called public and one is called private. You can encrypt using the public, but you can only decrypt that using the private key. That is how it works. In other terms, it's a famous analogy. The key that locks the door is not going to unlock the door. The key to unlock the door is a different one. That's how it works. That's how an asymmetric encryption works. Okay. This again, same thing. The key, the method that was used for getting this is not the same that can be used for getting back the original one, right? So what do you want to for a strong encryption? First is use asymmetric encryption where possible, like sophisticated algorithms like AES and RSA exists. RSA is asymmetric, AES is symmetric actually. Okay, but whenever possible, use asymmetric ones. They are much harder to break, and they're also very hard to actually compute. Okay, or you can use a combination of that. There is multiple uses where this happens. What happens is like RSA, since it is very heavy on the CPU, people use AES, but they encrypt the key used for AES using RSA and encrypt the key with public key and send it out and so on, right? The third is use encryption with larger blocks and bigger key lengths. I showed you, right? 250. If your input is 256 sorry, in this case it was the output. If the output is this, getting back to the original is going to be much, much, much harder, right? Same thing applies to encryption. If your blocks are larger and your key length is bigger, the encryption is stronger. And using all of this, it won't leave any patterns behind, okay, if you apply these. So now let's talk about the strength of encryption. Okay, if you go back to hashing, I think somewhere here I had written strength of encryptions, somewhere multiplication, and I told you about the primes, right? 17 is prime and 22 is factorized into 11 and 2 only, so 3 combinations. So I'm repeating that again. The same thing I've copy pasted over here. Asymmetric encryption is a bit similar in terms of how bigger is better rules play for numbers, and we have already shown you that example. For example, I gave you this. This is a multiplication. Okay, it's the result of a multiplication, but this is a big number, and just for you to see it in with commas, it's 15 digited, right? So it's like these are millions, billions, trillions, 404 trillion and 370 billion 674 million 460,539. That's what the number is. Was created by multiplying two large numbers. Okay, can you guess which two large numbers? Very difficult. You can start trying to factorize, and this is where the factorization problem comes in. What if I told you that both were 8 digits long? You still have at least what? 999999, and if I take an average, it would be something like 5000000. I think that many tries on an average to be done to find out the first factor, which will give you the second factor as well, right? So will telling you that the the numbers were 8 digits long going to help it a little bit, right? And what if I told you both were prime? So these two 8 digits, they do not decompose into anything else, right? So you have to go through that, I think 50 or 5 billion, I don't know how to say it in English, that many trials on an average, and maybe even, on this number, 99,999,999, this many. This is the max. But yeah, you might have to go to there, right? So bigger the number, the more the effort's going to take with these rules. Large numbers and prime numbers are going to give you headaches if you're trying to break it. And this is more or less how RSA works. Okay? How RSA works is it multiplies two very large prime numbers, gives you a number, and there is one key that is derived using this. Okay, and the other key is derived using another set of mathematical operations using the other factor. Now, since this number is so huge and this key gets derived from also a very large number and it's not traceable, okay, it's more or less a hash. Like if you converted this into a hash using a sophisticated algorithm, you can't get back to this, and it would only reveal this number, not this. You'll have to go through RSA's entire implementation. It's difficult for me to explain it in very simple manners, but yes, RSA's entire security, and it is one of the most secure algorithms, depends on the difficulty a computer has to go through. And well, for computer it's not exactly difficulty. What I mean to express is it's difficult to write an algorithm which can very fast, very easily decompose a large number into its composing factors, right? Now this is just what 1 2 3 I think it was 15 numbers, right? 15 digits. Now imagine a number that is 78 digits long or 128 digits long. This I believe is 1024 bits of the key size becomes 1024, so this digit becomes 78, and if you go to 409, I think that becomes 128, I guess, something like that. So yes, Increasing these number sizes is going to give you a bigger number, which is much more difficult to break, and that is how the modern encryption or cryptography standards stand. Okay, this again is a primer, very simple one. Sorry, let me drink some water. So that concludes more or less about encryption. I hope you read this. Okay, in terms of encryption, in the encryption lingo, plain text is the original text, cipher text is the modified or encrypted text. Cipher itself means the encryption methodology. Okay, now let's go to the GPUs and code breaking side. People say that GPUs are, uh, you know, they are used for breaking password. If someone has a GPU, they'll be able to break your password or some kind of encryption protection mechanism faster. Why? So we'll be using hashing as an example, but GPUs can be used very much the same way to try and break encryption too, because again, the amount of effort it takes to figure out what was the input to get the output here, right, is around the same it is going to take. I mean, it can be different. There are multiple factors at play here. But again, if you have to factor a 78 digit long number, I mean, come on, you'll have to go through a very large list of numbers to actually try and break it. Like, what are the factors you're going to guess, right? So, we are going to use hashing as an example here, but again, the similar approach can be used for breaking an encryption too. So, how do hackers break a hashed password, right? So, assume there is a database from which a password hash was stolen by a bad hacker. There are good hackers, but okay, for the for this document in this video, we'll just call this mean bad hacker with this term hacker. So you might have heard of so many security breaches happening. What happens is they somehow dump the database. Basically, dumping the database means making a copy of it, right? Most sensitive websites or services where you enter your password, they don't store your password. They store the hashed version of your password. So with the same password, again, like I said, the less number of collisions is the target, and so is this destructive way of removing parts. So with this same password, you'll be able to get the hash, but the password hash, which this guy has stolen, can't be used to derive the original password. Again, I'm revisiting this. If you have a longer password, you have a better chance at getting a good protection over here. So coming back, the hacker gets some password hashes from the database. Let's say he picks one, and for the sake of this video, let's assume that this is what he's looking for. So one of the ways of attacking this, there are various attacks. Two of the most popular are brute force and dictionary. The dictionary attack, what it uses human psychology more or less. What happens is when you are setting a password, you are going to set a password which is easy to remember. Some of the most used passwords are password and 1 2 3 4 5 6 7 8, something like that, right? So a dictionary attack, what it does, it has a list of such passwords, and it will try to break them. It will use a hashing mechanism, that algorithm. Send, this is to denote the chip, which is running the hashing algorithm. So this input goes in, this output comes out. This input goes in, another output comes out. This goes in, this comes out. And let us say, guess me, not or exclamation mark 1 2 3. This is what your password was, and it feeds it, and this password comes out. He's looking for this one, right? That's it. So this is the mechanism of dictionary attack. A list of passwords exist, which probably a normal human being would have used, and they go on trying, and if one matches, the hashing algorithm produces the same hash as this. It's, even if it was a hash collision, it's good enough, right? It will get to the service. He'll be able to break into your account. Now coming to brute force, right? Brute force is brute. it's brutal. It's it's like just go on, keep on trying random stuff, but in a sequence. That's what the essence of brute force is. So it starts with A, and let's say it goes to A B C D E F G H I J K L M N O P Q R S T, like that, and then it reaches and goes on and on and on, guess, and then it goes to guess me, not 1 2 3, and for all of that, these he's trying. Okay, he's not getting the result, but he's trying. And when I say this, let me expand it, what the actual scene looks like. So it starts with A, B, C, and then it goes to E, F, G, H. But it doesn't, just because your password is G, the encryption or the hashing mechanism doesn't know that something starting with G is going to get me this. So it goes to G, but it proceeds. Goes to E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, Y, Z, and then it goes to A, B, A, C, A, D until A, Z, and then it will go to Z, sorry, B, A, B, 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 C, and so on. And it will go on. It will go on adding and trying and guessing. So it goes to guess, guess R, guess, guessed, and go on, because this won't produce this result either, right? And then it will keep on trying. It will keep on trying everything till it reaches to guess me not 1 2 1, 1 2 2, 1 2 3. Bingo. Matched. Hash produced. Matches the desired output. Done. Now the thing with brute force is it is guaranteed to give you a result if you already have a hash and you can try unlimited number of times. Okay, which is why most places will only let you try for, let's say, 7 or 8 times or 10 times or something like that. If you're trying again and again, maybe you're trying to guess a password, right? So they don't let you try infinite number of times. This is the reason someone might be doing the brute force attack, right? All right, so these are the two ways. Now this might work, this might not work, and they're very similar, except that the sequence used here is generated using an algorithm, a method. Here it comes from a more or less a file which contains a list of possible passwords people use. All right, again, it's a numbers game. So let's say you had this password. Let's guess this is the password. This password is 1 2 3 4 5 6 7 8 9 10 11 characters long. It has got capitals, this G and M are capital. It has got small letters, U, E, S, S, and this E here, that is small. It is an exclamation mark, which is a special character, and has got 3 digits. So it has capitals, smalls, digits, and special. Now I said that brute force, since it is automated and in a sequence, is guaranteed to someday get you a match, right? So this is a guarantee. So you have to fight against this guarantee, right? So let's look at what the numbers say. So it has got capitals. How many capitals are there in English? And I'm only going to talk about English here. Of course, your password can contain some of the European characters or some of your other local language characters. I don't know what password you used where and what their policy was. Did they allow such characters to be present in the password? I don't know. I don't know any of that. So I'm going to assume that you used a fairly regular English keyboard with 26 capitals, 26 small characters in English, with 10 digits and approximately 20 special characters. There are more than 30 actually. But the thing is, you can't always type most of them, like not in all the scenarios, right? You might have seen some banks or some other institutions or other websites ask you to use a special character in your password, but they also restrict the number of special characters. So I'm just putting it at 20. So what does this get me? If a password is 11 characters long, okay, and has got all of this, how many combinations at max, okay, or an average? So if you mix in a password all of this, the possibility to have the total number of characters that you would have with a capital, small, digits, and special is 26 of these, 26 of these, 10 of this, and 20 of this, 82 possibilities. Here I'm getting only 3 smalls, digits, and special. You have got 56. If you are using only smalls and digits, right, you're going to get 36. And if you just type the word in all lowercase, 26. Now I'm assuming the password is 11 characters long, and on an average, this is at G, right? So if you follow this, okay, let's assume somewhere in the middle, you will be able to reach your desired guess, this password. So I'm going to divide the final maximum possible number with these many characters by 2, just to get a average sense, a very rough average sense of numbers or the count that you need to try before you can break this password. Something like this. Okay. So with all of these combined, you are going to get this many combinations. This is an average one again, as you can see, divided by 2. 56 gives you this, 36 different possibilities in your password gives you this, 26 will give you this number. Look at this number, man. That number is bloody huge. Okay, so let us assume a password hashing operation takes about 1000 CPU cycles. Okay, it can take more or less. I'm just making a guess here. Okay, and you have to remember 2 things about these. First, CPUs are really good with numbers. They're really fast with numbers. And when you're trying to guess, when you're trying to run a normal application, they might seem slow. That's because of the rest of the CPU architecture, the way things are designed. Something is resting on disk. It has to be brought in memory. That takes time. It has to be loaded into the CPU cache and then into the registers, and that takes time. And the whole input, output, and painting things on your screen. All of that takes time. But when you're trying to break a password, you're just computing number. You're just number crunching. And CPUs, with their the last 50-60 years of evolution, they have become really, really good with all of these operations, this multiplication and shuffling and placing this thing there and so on. They have become really good. So it is not an oversight to say that 1000 CPU cycles would be able to get you a password hash with a fairly simple one, a very simple algorithm. So I'm going to assume that 1000 CPU cycles is what it takes for trying out one password. Okay, hash operation, or one single hash operation is going to take 1000 CPU cycle. Now, most modern CPUs are around 2 gigahertz. Some are less, some are more, but with turbo and power consumption and type of device and so on. Let's just assume it's at 2 gigahertz. That means about 2 billion cycles per second. Which means if you divide it by 1000, you have got 2 million. So one CPU will be able to attempt 2 million password guesses per second. For an 11 characters password made of only lowercase characters, which is this, it will take this many seconds, this many hours, this many days, this many years. 29 years. That's still long, right? But you have to consider that most processors that you'll get in any fair laptop that you get, buy, or a phone, they'll have 4 cores, right? Even 8 core processors are not very uncommon now. You can easily get an octa-core processor. Let's assume it has got 4 cores. What happens to the numbers? It goes to 6.6. Okay, approximately. So you have got 4 CPUs trying to break the password, 2 million operations, 2 million guesses per second. It will take approximately 7 years to guess your 11 character password made of only small characters. Okay, and this is what more or less happens, right? You're taking one guess, giving it to core. Oh, why is this at here? I should place it here. Okay, you are putting one password input into one core, running the algorithm, getting a hash, and you're just matching, right, against the desired hash. And this is what happens. So potential password count for all characters included is much larger than the potential password in the case of this one, 82, right? Here I'm going to find out what is the difference between this and this, right? How many, what is the complexity? So the total number of guesses for the password, which is still 11 characters long but has got all the mixture of capitals, smalls, special characters, is about 300,000 times more complicated. It's going to take 300,000 times of effort to break a password which has got all of the capitals, smalls, digits, and specials. That's what I'm trying to convey here. So even if you can attempt 2 million passwords per second for 11 character password made of capital, small, digits, and special characters, it will still take 2 million years. I'm talking about a 4-core processor. Lovely. And now we are going to talk about why GPU crushes those numbers. This is the address. You can go and check it for yourself. And this is the spec for RTX 5090, which is currently the most powerful graphics processor available in the market for a consumer. You and I, normal people, can get it. So I'm going to just use this. Obviously, there are more, better, bigger graphics processors available to enterprises which are not sold in the open market. But you can see this, right? There are 21,760 cores. We were talking about 4 of a normal processor. This guy has 21,760 processors. You can see the boost clock is 2.4 gigahertz and the base clock is 2. I wasn't very wrong when I assumed this, and trust me, I assumed. I didn't go back and change all the numbers. Where did it go? This one. Right? So holding those assumptions, that is not a number, that is a threat to security. It can try everything 21,760 times faster. If you look at brute forcing, in one cycle, the first core would be trying out the hash of A, the last core would be trying a hash of 4 charactered string. This is how fast it will move. And all small letter password for 11 characters can be broken in under 4 hours. What were we talking about? 29 years. 7 years. This guy will break it in 4 hours. 4 hours flat. Password with 11 characters with mixed small capitals, digits, and special characters will now take 92 years only. That still looks like a big number, right? But I mean, someone using a graphics card for 92 years straight to break a password, good luck. I mean, the guy whose secret you wanted to reveal has died already. Great. But that's one card. What if someone has 100 of those, 10 of those? This number gets reduced, right? And in the most complex case, it gets solved in less than a year. 100 of those. I mean, when the Bitcoin revolution was still on, people were renting and buying hordes of GPUs, and I remember reading about someone who had to stop his center because he was using a nearby lake as a cooling solution, and it increased the average temperature of the lake, causing some fish to die. I guess that's what happened. People have hundreds of these, thousands of these. That some people do have these, right? And when you have this, the more complex case, this one, 11 characters, all small, capital, digit, specials, all mixed, gets solved in less than a year. And in the case of all lowercase one, you can forget about it. It will take about a minute. If you have got hundreds, it will take a minute to break. And this is assuming this is the technology we are using. What if NVIDIA comes with another card with double the capacity? What then? And what about APTs? And I'm not talking about DB. Here APTs mean advanced persistent threat. Basically, an attacker who has got advanced hardware, it is a threat. It intends to break into your account and steal stuff from you, and it's persistent. it has got financial backing in one way or the other. That is what an APT is. So an APT with all of this and you using a bloody weak password, you are done and dusted. 1 minute is what it will take. And this is why GPUs are feared, because of this parallelism. Okay, this. You see this? This is why they are lethal. So, GPUs are not silver bullets, not even close. GPUs have a certain architecture. Okay, and you can use that architecture of a GPU against it to create hashing and encryption mechanisms which cannot be broken using a GPU. And I will talk about that in another video. I am right now speaking since I don't know since how many minutes. I'm kind of tired. I hope this was useful. I hope this was, you know, educational to you, because this took a lot of time to create in a way that could be easily explained, and all of this took quite a bit of time. I would really appreciate if you could like the video, share it with people who might need it, and subscribe would be good. Again, only do it if you understood stuff. If you have got questions, ask me. In one way or the other, you can go to techrail.in. You'll find the ways to reach us, the entire community, including me, in the contact page. If you go to, you can go to my site and you can use contacts a link, or you can go to techrail and you can go to contact links and you can ask at one of these places. Okay, I would prefer Discord. Alright, I guess that's it. Thank you for watching if you did watch, and see you again. Bye.